So in this class, we will discuss about an analysis problem on beam columns. In the last video, I have explained the steps which we have to follow in the analysis of beam column. So here, this is the given example. So you have a beam, another beam like this, connected to a column section. This is the plan. So by welding, the load coming on this at this not the load, it is the reaction. Reaction coming at this junction is 225 kilonewton. Reaction at this junction is 375 kilonewton. In addition to that, due to the loads coming from the top floors, there is an axial compressive load of 675 kilonewton at this point, at the center of gravity of this column section. So this column section is ISHB 300 at 618 Newton per meter. Now the question here is, we have to check the adequacy of this section to take care of this axial load as well as this eccentric load. These two are eccentric loads. You can see here, so those eccentric loads can be explained here like this. This is the column, this is the elevation. So you have one beam junction here, another beam column junction here. This is the center line of the column where the axial force from the top stories is 675 kilonewton, which is given. So all these values are factored values. That means these reactions they are calculated due to the factored loads acting on the structure. So 375 kilonewton and 225 kilonewton, they are the axial force, they are the eccentric forces acting. And eccentricity here is 150 mm because the total depth is 300 mm. So this will be 150 mm and this will be 150 mm. So this is how we can represent the loads coming on the beam column. The end reactions from beam 1 is 225 kilonewton, end reactions from beam 2 is 375 kilonewton. These are the factored values. So these values are same at the bottom also. At the bottom of the column also, so it is subjected to same type of loading. So that's what he has given. So both at the top and bottom, you have the same type of loading. And the axial compressive force coming from the top stories is 675 kilonewton. The effective length of the column is 3.2 meters about both the axes. About both the axes means about both z axis as well as y axis. This is the y axis. About both z and y axis, the effective length remains the same. So the question is, check the adequacy of the section. So whether the beam column section ISHB 300 which is provided can take care of those forces. That is the thing. So what you have to do is, first you have to calculate the actual compressive force coming on that beam column, compressive axial force coming on that beam column, and also the moment due to the eccentric loads. So here this beam column has to be designed for a total load of 225 plus 375 plus 675. So that is 1275 kilonewton. That value I am going to take as n. Then moment also will be there because these are eccentric loads. So you have to take the moment about this point. So moment due to this will be 375 into kilonewton into 150 mm. So this can be converted to meters, which comes out to be 0.15 meter. So 375 into 0.15, that is clockwise. And the moment due to this 225 kilonewton will be anti-clockwise, therefore minus 225 into same distance. So 0.15 meter. If you simplify that, it is 22.5 kilonewton meter. So this is the moment that is acting both at the top and bottom. So because he has given same load pattern at the top and bottom also, so whatever load acts at the top of the beam column will be the same as the bottom of the beam column, and whatever moment acts at the top will be the same at the bottom. So here, so since you can have the buckling in one, we will take the buckling in one direction, something like this, single curvature buckling. So therefore, moment will be like this, moment will be like this, at both the top and bottom. That is 22.5 kilonewton meter is the moment, and axial load is 1275 kilonewton both at top and bottom. So this is how we have to calculate the compressive axial load acting on the column as well as the moment. So here of course it is a uniaxial a moment. So there is no value of my here, only mz is there, n and mz will be there. So first step we have to write down the properties, because this is an analysis type of problem. Section is already known. You have to check the adequacy of the section. Write down the properties of the ISM 300 at 618 Newton per meter from steel tables. So A is nothing but AG here. So gross area and effective area of that section is same, 8025 millimeter square. Radius of variation along z axis is 127 mm. RZ. RY radius variation along y axis 52.9 mm. Total depth of the section is 300 mm H. Then width of flank 250 mm. Thickness of flank 10.6 mm. Thickness of web 9.4 mm. Radius at root is 11 mm. So these are the details, and of course ZPZ, that is the plastic section modulus of the section, 962.18 10 power 3 millimeter cube. Elastic section modulus about z axis 863.3 10 power 3 millimeter cube, and moment of inertia about z axis 12,950.2 10 power 4 millimeter power 4. Moment of inertia about the y axis 2246.7 10 power 4 millimeter power 4. And now we have to calculate this d, depth of web, which is h minus 2 times tf plus r1, which comes out to be 256.8 mm. So these are the geometrical properties of the given ISHP section. Now next step is you have to check whether the section is plastic or compact or semi-compact. So for that we have to check for both flange and web. So for the flange it is B by TF. So B is half of BF. So 250 by 2 divided by 10.6. Of course all these are available in table 2, page 18 of the code. So this I have already explained in the design of beams. Table 8, page 18 of the code, IS 800. So since here you can see that 11.79 we have got epsilon is 1 here. Epsilon is given by root of 250 by Fy, which comes out to be 1. So it is less than 15.7 epsilon. So that this will be in the semi-compact category. So please refer the table for categorizing that. So it is less than 15.7 epsilon, so semi-compact. Whereas coming to the web, it is d by tw ratio. D is 256.8 divided by 9.4 is tw. It is 27.3. It is less than 87 epsilon. So therefore, it is a plastic section. Now, flange is semi-compact, web is plastic. Therefore, the section we have to consider the having least strength, that is semi-compact. So least one we have to take. So semi-compact is the section. Now when it is semi-compact, the value of this beta b will be ZEZ divided by ZPZ. So this you have to keep it in mind. Suppose if it is plastic or compact, then beta b will be equal to 1. So these things I have explained in the design of these. Now after taking the section classification, as I already explained in the earlier video, so you have to check for 4 criteria here. So adequacy has to be checked for 4 criteria, out of which the first one is check for local capacity of section. So local capacity means, of course, whether it takes up local buckling, crippling, all those things. So for that we have to use an equation which is given in the code in page number 71. There is an equation, n by nd plus mz by mdz should be less than or equal to 1. So that is the equation. So here, since my is 0, so this equation we are using because in this problem moment is acting only along one direction, along z direction. So it's a uniaxial bending case. Now here n is this value. To check that we need 4 values here. N is this 1275 kN total actual load acting on the column, and then ND we have to calculate using this formula. It is the design compressive strength due to yielding. So AG into Fy by gamma MO. So AG is this value of that section, area of the gross area of the section 8025 into 250 MPa is Fy divided by 1.1 is gamma MO. So you are going to get the value in newtons. So then you can convert it to kilonewton, 1823.86 kilonewton. Similarly, I will this MDZ. This is the design bending strength. Design bending strength is given by beta b into ZPZ into Fy by gamma MO. See here, this takes care of the compression, this takes care of the bending effect. So ZEZ, so beta b, since it is a semi-compact section, beta b is ZEZ by ZPZ into ZPZ into Fy by gamma m0. This gets cancelled. So now you will be having ZEZ into Fy by gamma m0. ZEZ for that this section is 863.3 to 10 power 3 into Fy is 250 divided by 1.1. You simplify that, you will get this much Newton millimeter. You can convert it into kilonewton meter by 196.2 kilonewton meter. So this is MDZ, this is ND, this is N, this is MZ. Now you know all the four values. Substitute in this and check whether you are going to get the sum of the ratios less than 1. So your value of N is 1275, ND is 1823.86 plus MZ is 22.5, that is MZ, divided by 196.2. So if you add these two ratios, you are getting 0.813, which is definitely less than 1, therefore it is safe. So the first check is carried out. Now the second check is check for member buckling resistance in compression. So we have to now consider the compressive effect now for the beam column. Since beam column is subject to both compression as well as bending, so now we have to check for member buckling. So here H by BF ratio we have to take. H by BF ratio, here it is 300 by 250, 1.2. Now we have to refer this table 10 in page 44 of the code. So this is the table we have to refer. So once you get these two, so this is less than or equal to 1.2, TF value is 10.6, it is given, it is less than or equal to 100 mm. That means according in the table, you can see in the table 10, so if these two criteria are there, then we can decide about the buckling curve. So in this case, Ry is 52.9, which is given here, Rz is 127 mm. So Ry is less than Rz here, radius of variation about y axis less than radius of variation about z axis. So based on the buckling curve, so if you take z axis, if the bending takes place about z axis, then it is buckling class B we have to take, buckling curve B we have to take. If it is about y axis, then buckling curve C we have to consider. Now let us check for both. So lambda y, I take lambda y as this, or you can take it as just take the ratio, because one more term we are going to use later. So you take this ratio KLY by RY. So KLY by RY, KLY is the effective length in y direction. It is 3200 mm, 3.2 meter. Divided by RY is 52.9. Take the ratio 60.49. This is a standardized ratio. Now for curve C, about y axis is curve C. So what you have to do is refer the table which is given in page 42. So you have to refer the table. There is a table already given in page 42 of the code. So in that table, so depending on the value of Fy and KLY by Ry, so for KLY by Ry is equal to 60.49 and Fy is equal to 250 MPa, the corresponding value of bending stress. So this is bending compressive stress. You can say bending compressive stress FCD about the y axis will be 167.2. Of course, you have to interpolate this. So this, of course, this procedure is adopted in the design of columns in your undergraduate level. Then your design compressive load in y direction is given by design compressive bending stress in y direction multiplied by the area. So stress into area gives the force. So if you substitute and simplify, you get 1341.9 kilonewton. That is 167.216 Newton per mm square into this value. 8025 millimeter square. You are going to get in newtons, then you can convert it to kilonewtons. You are going to get PDY as 1341.9 kilonewton. It should be greater than the actual load coming on the column, which is 1275. So it is greater here, therefore no problem, safe. Similarly, you can check in the z direction also. Take the ratio KLZ by RZ. KLZ is once again effective length is same in both the directions, 3200 divided by RZ is 127. So ratio is 25.196. Now only thing is you have to refer curve B, because curve B for about z axis is given in the code. So you have to refer the table which is given in page 41. Page 41. and you have to interpolate, you will get FCD Z value as 220.32 Newton per mm square, and the corresponding value of that is design compressive strength. D means design compressive strength along Z direction will be FCD Z into AE. So definitely this will be greater than whatever we have got for this PDY. So PDZ is greater than PDY. So it is also greater than 1275. Therefore, what you can say, this is same. This is same. That means what you can observe here is, if this value KLY by RY value is more. See here, KLY by RY is more than KZ by RZ. 60.49 is greater than 25.196. That means if this value is more, its strength carrying capacity will be less. So if the slenderness ratio is more, strength carrying capacity will be less. That means when the column becomes longer, so its strength carrying capacity will be less. So this is the second check we have to do. Next, third check. We will go for the third check now, because we have to check for 4 criteria. So 2 already we have checked. Now we will go for the third check. The third check is called as check for member buckling resistance in bending. Check for member buckling strength in bending. See, this all these steps I have explained in the previous video. So for this, of course, now we are treating the beam column as a beam now. So what we are doing is, first check is for local capacity, second check is treating the beam column as a column, third check is treating the beam column as a beam. Now for this we have to calculate, as we have designed in the case of laterally unrestrained beam, we have to calculate one thing called as MCR, which is called as the lateral torsional buckling moment. The MCR we are going to calculate, lateral torsional buckling moment. So this value we have to calculate. So for this we have to use the same formula which is given in page 54 of the code, which we have used in the case of laterally unrestrained beams. Only thing is, it should be multiplied by a factor called C1. So C1 into root of pi square E into Iy divided by LLT square into GIT plus pi square E into Iw divided by LLT square. So this is the formula which we have to use for checking the flexural strength. Now here, once you know all these values, of course E value you can take for steel as 2 into 10 power 5 Newton per mm square. Iy value for the particular section which we have assumed that it is already written. So what is the value of Iy? So Iy is here 2246.7 into 10 power 4. 2246.7 into 10 power 4 millimeter power 4. Then LLT is nothing but the effective length of the column. It is nothing but 3200 mm. So please note that everything should be in newtons and millimeters. Then G value, of course, for steel you can take 76.93 into 10 power 3 Newton per millimeter square. Better you remember this value for steel, E and G values. Then the IT value, of course, is torsion constant, which is given by summation Bi TiQ by 3. So once again, how to calculate this I have explained. For the flange, we have to take Bf into Tf cube by 3. Of course, this should be multiplied by 2 because there are two flanges per dissection, this one and this one. Then plus, for the web portion it is total depth minus Tf, that becomes the effective width of web, into Tw cube divided by 2. Now substituting the values here for Bf, Tf, all those things, and if you simplify, you will be getting, of course, Bf is now, if you substitute 2 into 250 into Tf is 10.6 cube by 3 10.6 cube by 3 plus 300 minus 10.6, correct? So 300 minus 10.6 into the value of Kw is 9.4 cube. So 9.4 cube divided by 3. So 2 stands for there are 2 flanges. If you simplify this, you will be getting the value 27.86 into 10 power 4. 27.86 into 10 power 4 millimeter power 4. So this is the torsion constant. It is called as the torsion constant. Then one more constant we need, that is IW, which is called as the warping constant. So all this you have done in the case of design of laterally unrestrained beams. So warping constant we have to calculate IW. That the formula is given in page number 129 of the code. So warping constant is available in page number 129 of the code. IT is available in page number 54 only. So this all this I have explained in the design of laterally unrestrained beam. 54 only this formula is available. Next, coming to page number 129, you can use this formula for calculating IW, which is 1 minus beta f into beta f into Iy into hf square or hy square. Here this hy is nothing but h minus p. That is you can take it as 300 minus 10.6, which is it comes out to be 289.4 mm. That is hy. Iy value of course same thing, 2246.7 into 10 power 4. Then beta f of course is 0.5 for symmetrical section. For symmetrical I section. Okay. So if you substitute these values in this and if you simplify, that is 1 minus 0.5 into 0.5 into 2246.7 into 10 power 4 into this value, that is 289.4 square. If you simplify this, you will be getting a value of 4.7 into 10 power 11. It's a big number. 4.7 into 10 power 11 millimeter power 6. Please note that this is the unit. So this is the unit of IW. Now you have to substitute all these values in this expression. Substituting the values in 1. So you will be getting, and the C1 value of course. C1 value you can get from the table which is available in page number 129 only. So C1 actually is equal to 1. So this is because uniform moments are acting at both the ends. Uniform moment is subjected to this column, is subjected to uniform moment here and here. So both are equal to m only. That means your m1 and m2 values, they are equal here. So therefore your psi value will be equal to 1, which is m2 by m1. Since they are equal, it is actually equal to 1. So since these two are equal, so the C1 value becomes 1. So this is available in page 129. So you should remember the page numbers. Once you remember the page numbers, you need not remember anything. So directly you can refer that page and you can get. Now substituting the values, you will get MCR is equal to C1 is 1 into pi square into 2 into 10 power 5 E value into Iy value 2246.7 into 10 power 4 divided by 3200 square. So this is what, of course, this is what you will get in brackets. So this is 1 into, so this will come in brackets. Continue with that. So you will be left with G into IT. G is 76.923 into 10 power 3 into IT value is 27.86 into 10 power 4. So this is one term plus pi square into E is 2 into 10 power 5 into IW. IW is 4.7 into 10 power 11. 10 power 11 divided by 3200 square. So this entire thing is under root. Please note that this entire thing is under root. If you simplify this, you will be getting MCR as 6.965 into 10 power 8. So MCR 6.965 into 10 power 8 Newton millimeter, or if you convert it to kilonewton meter, it will be 696.5 kilonewton meter. Okay, 10 power 6 if you take here, it becomes 696.5 kilonewton meter. Anyway, we have to substitute in Newton millimeter only. So after this, so refer the same this thing in page 54. In page 54, you have to calculate some of the parameters: lambda, LT, phi LT, xi LT, FBD, and finally MD. So that's what we have to do. It is similar to design of unrestrained beams. So what we have to do here now, once again page 54, you have to calculate these parameters: lambda LT, phi LT, xi LT, then FBD, then you have to get MDZ. So these values we need. So if you substitute these values, lambda LT, which is a non-dimensional straightness ratio, it is given by square root of beta B into ZPZ into Fy by MCR under root. See, this is the formula which is available in the code. Now of course here beta B is once again ZEZ by ZPZ. So ZPZ will get cancelled. So you will be left with ZEZ into Fy by MCR under root. So if you substitute the values and simplify in newtons and millimeters, you are going to get the value as 0.556. Please do that. 0.556, which is greater than 0.4. Therefore, the thing is, we have to consider the effect of lateral buckling. Next is phi LT. So this phi LT is given by the formula 0.5 into 1 plus alpha LT. So 0.5 into 1 plus alpha LT into lambda LT minus 0.2 plus lambda LT square. Once again, the same page is available. Here please note that this alpha LT value is for a rolled section, it is 0.21, for a welded section it is 0.42. Once again here, so if you substitute all the values and simplify, you will be getting phi LT value as 0.6919. Then xi LT. So xi LT value is given by 1 divided by phi LT. So the xi LT value, so I will write here, xi LT is equal to 1 divided by phi LT plus phi square LT minus lambda LT square to the power of 0.5. So everything is available, all the formulas are available in the code in page number 54. If you substitute and simplify, you will get 0.906 as ZLD. So these are the parameters we require. Next, after this, FBD. So FBD is the bending stress. So design bending stress, FBD, ZLT into Fy by gamma m0. ZLT into Fy by gamma m0. So ZLT is 0.906 into Fy substituted by gamma m0 is 1.1. If you substitute that, you will be getting 205.89 Newton per mm square, and finally you can get the value of design bending strength of that particular section, MDZ, which is nothing but FBD into ZPZ into beta B. So beta B into ZPZ. This is the value. So once again you substitute FBD as 205.89. Beta B is ZEZ divided by, so of course these two if you multiply you will get ZEZ. So that means FBD into ZEZ will give the value of MDZ. You are going to get in Newton millimeter. So finally you can convert it to kilonewton meter. So you are getting 177.77. 177.77 into 10 power 6 Newton millimeter, or 177.77 kilonewton meter, you can see that this is definitely greater than your applied moment md, which is 22.5. So therefore it is safe. So this is the check for the third check we have to do for bending, and the last check, fourth check. So all the four checks you have to do here. So the last check, since it is subjected to uniaxial bending, the fourth check will be the last check is called as the check for overall member buckling resistance. Check for overall member buckling resistance. Check for overall member buckling resistance for combined bending and axial compression. For combined, that means we are combining now. For combined bending and axial compression. Axial compression. That means what we have done here is, so we have treated the beam column as a column separately and a beam separately. We have checked for the compressive strength as well as the bending strength separately. Now we are combining both the effects as a beam column. So for that, you have to refer the equations which is given in page number 71 of the code. And please note that this is a uniaxial bending case where only moment is given in only one direction. So my is 0 here, mz is 22.5 kilonewton meter. So these things we should keep it in mind. If it's a biaxial bending, both my and mz will be there. Now here the corresponding equation here is P by PDZ. So you just see the page number 71. In that he has given the equation. So wherein you have to take my value as 0. So P by PDZ. So you refer that page, P by PDZ. P by PDZ plus KZ into CMZ MZ plus KZ into CMZ MZ divided by you have MDZ. This should be less than or equal to 1. Less than or equal to 1. There are two equations of course given in page 71. Out of this we are using the second equation. So because my is 0, we are using the second equation. So this is the equation. This should be satisfied. Here you know all these values. P value, P dz, P is nothing but n. Please note that P is nothing but n, which is 1275 kilonewton. P dz value also we have found out. What is that P dz value? 1768.06. 1708.06 kilonewton. That is P dz value. Mz value is 22.5. That is the given moment kilonewton meter. Mdz value just now we have computed, which is 177.77 kilonewton meter. So these four values we got. Now only other two values we have to calculate. That is Kz and another one is CMZ. So Kz is once again given by the formula which is given in same page. So Kz is equal to, you can note down, 1 plus lambda z minus 0.2. 1 plus lambda z minus 0.2. Okay, 1 plus lambda z minus 0.2 into P by PDZ into P by PDZ. So this is the equation, expression for Kz, and the thing is this should be less than or equal to 1 plus 0.8 into P by Pz. The condition is this should be less than or equal to 1 plus 0.8 into P by PDZ. So this we have to check now. Let us see what are the values now. So of course here lambda z is given by. So there is another expression for lambda z. So lambda z is given by square root of Fy by Fcrz. See all these things you have to calculate. like this. Okay, Fy is 250. Of course, Fc or Z is given by another expression which is pi square E by K Lz square divided by Rz square whole square. So this is the value of FCRZ. That is the critical stress which is acting along Z direction. Now if you substitute all the values and simplify, you are going to get this FCRZ value as 3109.32. 3109.32 Newton per mm square. You substitute that FCRZ here, Fy you take it as 250, and if you simplify you get sigma lambda Z as 0.2835. 0.2835. Then that if you substitute here, you will get the value of Kz as you will be getting Kz is equal to 1.06. 1.06. You are getting Kz as 1.06. Now you got this value. Now CMZ, another value, CMZ we have to get. That CMZ you can get from the equation which is given in page number 72. So another thing is here that should be less than, that you have to check now. This 1.06 whatever you have got this value, it should be less than this value, that is 1 plus 0.8 into P is 1275 which is equal to N divided by PDZ is 1708.06. So take the ratio, multiply by 0.8 and add 1 to that. So you will be getting that value as 1.576. 1.576. Naturally, this value, whatever we got 1.06, so it is less than 1.576. Therefore, that criteria is satisfied. This criteria is satisfied. Less than or at most equal to. Now, we need only the value of CMZ now. That CMZ is given by whatever is there in page number 72. Page number 72, he has given that CMZ value, expression for CMZ. That is the last check we have to do now. So CMZ is equal to, that is called as equivalent uniform moment factor. CMZ is called as equivalent uniform moment factor. So this is given by the expression. There is an expression to find that 0.6 plus 0.4 psi z. 0.4 times psi z. Please note that here psi z is something but 1 here, which because it is subjected to uniform moment on both sides here. So these two are equal here. M1 and M2 they are equal. In that case psi z becomes 1. Therefore, if you substitute that, CMZ becomes 0.6 into 0.4 into 1, which is 1 itself. So CMZ value is 1 now. So it is 1. So therefore, it should be greater than or equal to 0.4. That is checked. It should be greater than or equal to 0.4. It is greater than or equal to 0.4. In that criteria it will come. So therefore, now what you can do here is you substitute all these values in this. So if I take this as second equation, substituting all the values in equation 2 or expression 2. So what you will get, P is 1275 divided by P dz is 1708.106 plus Kz is 1.06 into CMZ is 1 into Mz is 22.5 divided by 177.77. If you add these two, you are going to get the value as 0.855, which is definitely less than 1. Less than or equal to 1 you have to get. So that condition is satisfied. Therefore, it is satisfied. Condition is satisfied. Safe. So all the 4 checks we have done here. What we have done is, first we have checked for the local capacity of the section, second check is for the compressive strength, third check is for the bending strength, fourth check is the combination of both compression as well as bending. That too in this case it is uniaxial bending because moment is given in only one direction. If biaxial bending is there, both My and Mz will be there, and two equations we have to take here. So there are two equations. Second equation also we have considered here. First equation also we have to consider if it is biaxial bending. So this is how we have to check the adequacy of the given section. It's a type of analysis type of beam column example. Okay. So we should be careful. Page number 54 we are using. Then tables, two tables we are using. Then we are using 70, 71 and 72. So those pages in the code we are using for the design and also analysis.